All right, in part B, we have secant squared x over 2 and tan x over 2. So secant comes with an even power and tan comes with an odd power, which is the power of 1. All right, let's go back to our guidelines here. So let's see which one is more applicable here. We have two items. We have secant squared and tan. I think number one is very good to apply. Secant squared, tan, right? Yeah, so what I'm going to do here is that I'm going to save secant squared part for dx. And well, then I'm going to have only tan. So it's still a simple u substitution problem. I don't even need to do this application of the Pythagorean theorem replacing secant squared x by 1 plus tan squared x. I don't need to do that. And you will see why. Well, I'm going to call u to be tan x squared right off. So essentially tan x over 2 and secant squared x over 2 dx is right here, right? I'm going to call u to be tan x over 2, and du would be what? So I'm going to apply the chain rule here. The outer function is tan. The derivative of that is secant squared x over 2, and I have to multiply this by the derivative of inner part, which is 1 half, and dx. Okay, good. So now this integral turns out to be, so first of all, secant squared x over 2 dx is equal to 2 times du. So I'm going to replace that by 2 times du. And tan x over 2 is just u. So in turn, I have 2u du. So even in this case, I didn't need to rely on to the guidelines all the way. I just got the idea that if you have the even power of secant squared, you can use 1 secant squared, or say 1 secant squared for dx, and with the leftover terms, you can apply the Pythagorean theorem. But I don't need to have any. I don't have any leftover term for which I can apply the Pythagorean theorem for. So at the end of the day, just one u substitution is enough, and it's 2u du to be integrated as u squared over 2 plus c. Boom, you got the result. So tan squared x over 2 divided by 2 plus c is the value of this integral. Another way to handle this problem is you can reserve secant x over 2, tan x over 2 for dx, and then you're left with only secant x, and you can call u to be secant x, and you can get a similar result at the end. And you can write down the final value in terms of secant squared, which is okay because tan squared and secant squared are related to each other by Pythagorean theorem. And that c here is an arbitrary constant. So the difference between my final result here with the other final result I just mentioned is just differing by a constant. So that the difference is just a constant. And that is hidden in the integrating constant c, okay? So I think that takes care of part B. I'm going to finish this video right now, but you will probably continue with part C, and you're wondering what I'm going to do in part C. All right, so let's finish the video. I'll see you there. Bye.